Assalamualaikum and good evening. My name is Nur Atika binti Muazmain, and together with my friend Halimah and Huri, we'll be doing some explanation on the lab we did for subject electromagnetic, which is wave. So for this lab session, we're studying about three type of wave. That is transverse wave, standing wave, and reflective wave. So for the procedure, for the transverse wave, we use the oscillator to produce the transverse wave, and we set it with no damping and have a medium tension with a fixed end first. Then we set the frequency to 1 Hz and the amplitude to 1 centimeter. And then we start the simulation. As we start the simulation, we'll be observing the wave behavior. And then we change the value of the frequency from 1 Hz to 3 Hz to observe what does the frequency affect the waves. And after repeating the process, we replace the fixed end with a loose end and no end setup. And then for standing wave, we use the oscillator to produce it. Also, we have it with no damping, but with high tension and a fixed end at first. Then we set the pulse width to 0.5 second and its amplitude to 1 centimeter. Then we start the simulation to observe what is standing wave. And then for reflective wave, we use the pulse to produce the pulse wave. We set it with no damping and have high tension. We use different type of end, that is fixed end, loose end, and no end. We still set the pulse width to 0.5 second, and later we will change it to 1 second, and its amplitude we fix it to 1 centimeter. For this reflective wave, we will observe the reflective wave behavior, whether it is reflected with inversion or without inversion, and does a reflective wave affected the size of the amplitude of the wave. So we move to the result. So for transverse wave, when we start the simulation, the oscillator start to transmit the wave. And as we see for the result, the maximum peak or amplitude of the wave is the same as we have said earlier, that is 1 cm. The length for 1 cycle is measured to be 3.8 centimeter long until it reach the fixed end. The wave will reflect it back and move towards the oscillator, but there is changes to its amplitude, which is amplified to 2 centimeter. We use the reference line and the ruler to measure the changes to its amplitude and the length of for the 1 cycle. However, after it is reflected, the wavelength remain unchanged, that is 3.8 centimeter long. Next, we keep the simulation ongoing to see what does the fixed end affect the wave transmitted and the wave reflected, and it shows the wave grows bigger in its amplitude as they go through and through the oscillator and the fixed end, while keep the length of the cycle the same. Next, we change the frequency to 3 Hz, but we still use the fixed end. So what we observe here is when we change the frequency from 1 to 3 Hz, the result of the observation was measured, length for one cycle is shorter compared to the previous setup, which is 1.22 centimeter. So figure 5 shows the difference of 3 Hz setup. And the other result for the wave are the same with fixed end, where the wave keep on increasing in amplitude. Here. Next is we're changing the end type to loose end. Loose end with 1 Hz. As we start the simulation, the oscillator still produce a wave of 1 centimeter amplitude with 1 Hz frequency. The measured length for the one cycle is still the same. That is 3.8 centimeter because we use the same frequency. In figure 9, here shows the amplitude also grow double the original peak, that is until 2 centimeter. Then when the oscillated wave collide with the reflected wave, it forms a non-uniform waveform, and the amplitude will reduce back to 1 centimeter, as we see from the figure here. And it can get even smaller at time without changing the length of the one cycle. And the same result shown when we change the 1 Hz to 3 Hz frequency. The result are still the same. When we change the frequency, the length changed only at the beginning. That is 1.22 centimeter and remain the same until the end of the observation. It's still resulting the same, that the amplitude getting bigger and then getting smaller back to 1 centimeter. But if we change the type of end to no end, where the wave is transmitted in without getting hold tightly or loosely, the result of using 1 Hz or 3 Hz does not give any changes. The amplitude remains at 1 centimeter peak, and there is no reflective wave, as there's nothing that holds the wave to reflect it back, the wave to the oscillator. So overall, we can conclude to this part of the task. Transverse wave is a wave that vibrates perpendicular to the direction of the propagation. And in the simulation, we can see that the dot will just move up and down at the same place. It doesn't shift it to the right or to the left. Next part will be explained by Halima.
Okay, thank you, Atika and Hurin. As for the standing wave, eh, eh. Okay, as for the standing wave, we know that a standing wave is a wave which oscillates in time, but the peak amplitude is not moving in a space, and the peak amplitude of the wave oscillates at any point in space constant, which time the oscillation at different points through the wave is in phase. So in the standing wave, we measured about at the fixed end by using 2 Hz. The result shows that the wave produced are much smoother and the amplitude is maximum for the first wave follow the parameter we have set at higher tension and fixed end. As the figure 18 shows, the result of ongoing amplitude will increase and decrease until at the time of reflective wave at the zero amplitude. Hence, the result shows that the new wave produced same rate and the time taken to this situation is only for 12 seconds. For the part of loose end, we still use the same frequency and we measured that the wave produced are much smoother and the max amplitude for the first wave follow the parameter we have set at a higher tension with loose end. So as it goes by, uh, the result of ongoing, the amplitude increase and decrease until the time of the reflective wave at the zero amplitude and the new wave produced at the same rate. So the time taken shows that the result at 9.43 seconds. For the last one, no end, uh, the result shows that simulation of when we apply high tension to the wave but have no end. There will have a standing produced because it is in existence of relative wave. So we can conclude that the standing wave is a vibration of a system in which some particular points remain fixed while others between them vibrate with maximum amplitude. So for the next one of reflective wave, I will pass to Hurin.
Okay, salam and hello, madam. I'm Hurin. I will present on the reflective wave. First, on these two figures, we have tried. For the first one, we have tried on the fixed and reflection. Uh, for these two figures, we set on the amplitude with 1 cm and pause width of 1 second with no damping and medium tension. Here we can see when we allow a pulse to propagate through the string, the pulse on the way to the right to the right end with the amplitude of 1 cm measured by the ruler. As we set the amplitude also at the 1 cm. Here we set it to 1 cm. Then on the right figure, for this figure, the pulse arrive at the fixed end. It exerts a force on the wall, and according to the Newton's third law, the wall exerts an equal and opposite force on the string. Then we can see here the pulse travel back along the string in the direction opposite to the incident pulse. The amplitude is the same, which are 1 cm, but it's more longer in wavelength. Okay, for this two figure, we try we try the same step, but change in value of the pulse width to 0.5 second. Here we set on Here we set on 0.5 second with 1 cm amplitude. We can see the same result as before, but the wavelength is much smaller. Here we can observe that the pulse width pulse width effect on the wavelength of the pulse means that if we change the value of the pulse width to the greater value, the wavelength also will be more greater. Okay, next we move to the loose end reflection. In this part, we set on 1 cm amplitude. with 0.5 second pulse width without damping and medium tension. In this case, for the first round, this is for the first round of the pulse wave uh, along the string. For the first round, the pulse arrived at the right end. The ring, this ring, uh, the ring, the ring moved up the rod, and as it moved, it will pull the string. For this, it will pull the string, and the string will stretching, and it will produce a reflective pulse with the same sign and amplitude as the incident pulse. Means that if this pulse wave move to this right end, it will reflected back to the pulse. Okay, next. When for this two figure, it is for the second round of the pulse wave. When it comes to the second round, the pulse move opposite to the first one, which the pulse shows an upside down wave, but still produce the same amplitude. As we said, the amplitude is for 1 centimeter. When it reached the loose end on the right, the pulse reflected also as in the first one. It's also reflected, but it's still the same as the incident pulse, which is upside down pulse wave. Okay, lastly, we move to the no end reflection. No end reflection. For this no end reflection, we also use the same parameter, which is 1 centimeter amplitude with 0.5 second pulse width without damping and medium tension. As we click here, we click on the pulse button, the pulse wave moving toward the right end with 2 centimeter amplitude produced by the by it lah. Then when it reached to the right, which is when it reached to the right, which is no end, the pulse become a straight line, means that the amplitude will become 0. So here we can observe that the reflective wave is changing in direction of the propagation of the wave that strike the boundary between different medium. Okay, this is we have done for the discussion, but we also attach this in our report. So that's all from our group. Thank you, madam.
Thank you, madam.
Thank you, madam.